In this video, we will discuss the concept of flux and the continuity equation. Flux, by definition, is the dot product between the area and the velocity. And usually, this is given the symbol large phi. It's also equal to the amount of volume of a fluid that crosses in a given time. So this is the rate of fluid flow. Now it seems strange to see an area with a vector sign, so let me explain that. If you have a surface that has an area like this, and we might normally think of base times height or length times width. What we're saying is that perpendicular to that area, we're going to make a vector. And that vector's length is going to be equal to the area, and its direction is perpendicular to that surface. And we're saying that if you had another thing, such as velocity of the water going like this, that would have an arrow as well. And what you would need to do is find the length of the area, that is how much area, times the velocity of the water, but you would also have to take into account the cosine of the angle. And the reason for that is that if you had a surface like this, but your fluid was flowing along the surface like this, then none of the fluid, none of the water, for instance, would actually leave the surface. On the other hand, if you happen to have it look like this, and your water was going this direction, a lot of water is passing out of the surface. And that's what this dot product is trying to do. It's trying to find the area times the velocity, let's make that a little v here, times the cosine of theta. Now, a lot of times at the trig-based physics level, the APB level, this angle here is going to be 0. And so we're going to say it's simply the area times the velocity. But it is the velocity part that's perpendicular to the area, i.e. aligned with this so-called A vector. And that's the way people do it in more advanced work. What is this thing flux? Flux is Latin for water flow. And it's trying to describe how much water is leaving out a particular surface. That could be the end of a garden hose. It could be the amount of water flowing across a point in a river. It's telling you the amount of water flowing. The Mississippi, for instance, has a great flow rate compared to a garden hose because it's much bigger. And what we want to do is to see what happens to the speed of a river as the depth or width of that river changes, or as you squeeze down, for instance, on the end of a water hose. So what we find is the following: how much ever water is flowing through one part of the river has to flow out of other part of the river. In other words, it has to be constant. If 50 gallons in 1 second comes in one side, 50 gallons in 1 second has to leave the other. Otherwise, it would build up in the middle. In order to keep flowing along, if you think about like a traffic jam, the cars coming in one side have got to push the cars out the other side. Otherwise, they'd all pile up. So this value, A times the velocity, is conserved, is constant throughout the problem. Considering the following pipe. In this pipe, a certain amount of mass comes in one side. So what we're really talking about is conservation of mass. You could say that density times the volume is fixed. This little piece of stuff coming in here is going to go through a particular delta x. And on the other side, a particular amount of water is going to go through this delta x. So this will be delta x1, and this is delta x2. This is area A1. This is area A2. So whatever volume of water that was in here, if it moves over that much water, this much water has to move out in the same amount of time on the other side. So let's see. Delta volume over change in time has to be equal to area 1 times delta x1 divided by delta t. But that also has to equal A2 delta x2 over delta t. And because we're talking about mass, all we needed for mass was to multiply that by density. So that's density, and that's density. And this is the amount of mass going per a given amount of time. So the amount of mass in a given amount of time, say 1 second, that comes into the pipe has to equal the amount of mass leaving the pipe. Now, if we look at these two parts here, you can see that the masses will cancel. I mean, the densities will cancel. So really, it's just the volume of the water. The other thing to notice is delta x over delta t. Delta x over delta t gives us A1 delta x1 over delta t is equal to A2 delta x over delta t. But that's just V. So this is A1 V1 A2 V2. So what is this equation telling us, this continuity equation? It says this. Let's say that you have, let me get up here somewhere where I got room on my screen. And there's some sort of lake or river. So let's take this river. In this river, there is a certain width and a certain depth. And there's a certain V. But if the river becomes shallower, then this goes down. That velocity has to go up. This is why rapids occur, fast-moving water, when it gets shallow. It also shows that there's some truth to the old wives' tale that says, still waters run deep. If the thing is deep here, then that makes the area greater. If the area becomes greater, if it goes up, then that means that the velocity has to go down. Now, it turns out that human blood moves at a particular speed, and when you get to a really high speed, the blood changes the way it flows. It moves from what's called laminar to turbulent flow. And turbulent flow begins to bang on the sides of the walls. So if you have a constriction, for instance, near the heart, the area goes down, the speed goes up, and it changes its flow. And that banging on the sides of the vessels creates a sound that you can hear with the stethoscope. And that's where you get heart murmurs from. So the measure of the heart murmur is really a measure of how fast the blood's going, and a measure of the speed of the blood going tells you about the area, and the area tells whether or not you have a constriction. Anyway, this idea that area times velocity is equal to a constant at all times in the river is known as the continuity equation. All right, I'll see you on another video.